Welcome to The Explainer. Today we're diving deep into the absolutely fascinating world of gas turbine-driven generators, but we're going to look at it through a very specific, kind of brutal lens, honestly. Perfect theory versus harsh operational reality. We're taking that clean, predictable math straight out of your textbook, and we're slamming it headfirst into the gritty, extremely high-stakes environment of the oil and gas industry.
To really wrap our heads around this, I want you to picture something with me. Set the scene in your mind. Imagine you're standing right on the deck of an FPSO, a floating production, storage, and offloading vessel, way out in the middle of the Gulf of Mexico. It's 2 a.m., pitch black, and you can literally feel the metal deck vibrating right through your boots. That vibration, that's the heartbeat of the entire platform. It's the gas turbine generator burning wellhead gas to push out every single watt of electricity that's keeping you safe and keeping the operation running. But think about the insane physical constraints of that environment for a second. It's 35 degrees Celsius out. The humidity is just suffocating, hovering right near 100%. And inside that casing, you've got a massive rotor spinning at exactly 3,000 RPM. I really want you to feel the stakes here before we even glance at an engineering formula. This machine literally cannot fail, but the environment around it is doing absolutely everything it can to strangle its performance. Okay, so here's our roadmap for this explainer. First, the heart of offshore power. Second, the Joule-Brayton cycle. Third, real-world power derating. Fourth, turbine maintenance philosophy. And finally, commissioning and final thoughts. Section 1, Heart of Offshore Power, the driving machine. Let's just dive right into it. For an offshore platform, the gas turbine isn't just an option, it's the absolute heart of the power system. Once you get above 1 megawatt, diesel engines just can't keep up, and the gas turbine takes the throne. Now, out on the water, aeroderivative gas turbines are your weapon of choice. Just like it sounds, these are basically born straight from aircraft NG designs. They give you this incredibly high power-to-weight ratio, which is massive because, every square inch of an offshore platform is unbelievably expensive real estate. They use a totally minimal floor area and are custom designed for single-lift modular installations. But there's a catch, actually a pretty massive catch. Because they run so incredibly hot and use an absolute minimum of metal to save on that weight, they hit you with super high maintenance costs and way shorter overhaul times compared to your heavy industrial turbines. It's the ultimate high-performance trade-off. Section 2, the Joule-Brayton cycle, theoretical perfection. Let's move on to the physics. So, moving from the practical deck space, let's look at the theoretical physics making all this power possible, the Joule-Brayton cycle. What's actually wild here is just how incredibly simple this foundational cycle sounds when you break it down into 3 steps. First, compress. You take ambient air and squeeze it to a super high pressure. Second, combust. You inject fuel and ignite it, spiking the temperature. And third, expand. You force that hot, high-pressure gas through a turbine, and as it expands, it spins the blades, turning the shaft. Compress, combust, expand. Sounds like a piece of cake, right?
But here is the shocking reality hidden inside that simple cycle. You'd logically think all that awesome rotational energy goes straight into your generator to make electricity. No way. Not even close. Roughly 50 to 60%, let's call it 55%, of the gross turbine output is instantly gobbled up just to drive its own air compressor. The turbine is literally cannibalizing its own power just so it can keep breathing. Only the leftovers, that 45% net shaft output, is actually available to drive your generator.
Section 3, real-world power derating. Physics fights back. Time to see what happens when the real world gets involved. We just looked at the perfect theoretical cycle. Now, let's watch environmental realities violently attack that theory. When you buy a gas turbine, the shiny nameplate rating is based on ISO reference conditions. That's a wonderfully cool 15 degrees Celsius, perfectly at sea level with a nice 60% humidity. It's basically a perfect spring day in a lab. But remember our FPSO in the Gulf? We're sweating it out at 35 degrees Celsius with suffocating humidity. Gas turbines breathe ambient air, and hot air is thin, less dense air. Less dense air means less mass flow through your compressor, and less mass flow simply equals less power. And the toll this takes is heavy. For every single degree Celsius, the ambient temperature creeps up above that 15-degree ISO baseline. You are losing between 0.5 and 0.8% of your generating power. Think about that. If you're 20 degrees over the baseline, you have instantly surrendered 10 to 16% of your platform's total power capacity, literally just because the sun came up and the air got hot. But hey, temperature isn't the only enemy out there. You also have to account for the universally accepted dirty engine loss. Over time, your engine is essentially vacuuming up particles. The compressor blades get coated in grime, combustion deposits build up, and the blades themselves actually erode, losing their perfect aerodynamic shape. This basic, everyday contamination will instantly rob you of an additional 5% of your total power output. Listen, if you don't bake that 5% penalty into your initial design phase, you're going to face some massive embarrassments when the machine enters service and just cannot pull the load. Section 4. Turbine Maintenance Philosophy, the ultimate defense. So how do we fight back?
How do we beat the heat and the dirt? Maintenance. And I don't mean maintenance as a chore. It is your ultimate, highly calculated defense mechanism. Picture a timeline stretching from 0 all the way out to 50,000 fired hours. You have to hit these exact intervals, dropping them onto your schedule with absolute precision. Right between 500 and 1,000 hours, you execute a compressor wash to strip away that 5% dirty engine penalty and get your aerodynamics back. Further down the timeline, at 8,000 to 12,000 hours, you do a hot section inspection, tearing into the combustors and high-pressure blades to make sure extreme temps haven't melted your metal. And finally, hitting right at 25,000 to 50,000 hours comes the major overhaul, where the whole unit is basically swapped out and rebuilt. Every single step is a surgical strike to restore efficiency.
Section 5. Commissioning and final thoughts. Let's bring it all together.
So once your maintenance is done, or if you've got a brand new turbine, you enter the final phase, bringing the beast to life. This is done through a totally non-negotiable, strict 5-step sequence. First, pre-commissioning, verifying every wire, every trip circuit. Second, first fire, a highly supervised ignition just to get her up to idle. Third, synchronization, where you have to perfectly match your voltage, frequency, and phase to the live bus bar. Fourth is the load test, pushing the power all the way to 100%. And fifth, protection tests, literally proving the unit will safely trip itself off if something goes wrong. Only after all that do you hand the keys over to the platform. All right, let's quickly lock in our essential takeaways from this explainer. Remember, your power output is going to derate by 0.5 to 0.8% for every single degree above 15 Celsius. You absolutely must budget for a 5% dirty engine penalty. You fight that dirt with a compressor wash every 500 to 1,000 hours. And you always bring the machine online with that strict 5-step commissioning sequence. So here is the crucial point I want to leave you with. Your gas turbine dictates the very life of your plant. It honestly doesn't matter how incredible your electrical systems are if the prime mover fails. When that tropical temperature spikes and your engine starts choking on dirt and salt, textbook theory isn't going to save you. Only your operational discipline will. Will your maintenance philosophy be enough to keep the lights on? Think about that the next time you feel a turbine spinning up beneath your feet. Thanks so much for joining me on this explainer, and keep learning.